Today we'll take a look at two ideas combining functions using this time division and composition of functions. So this looks kind of like the addition, subtraction, multiplication we've discussed previously, but with two functions we can also calculate the quotient of the two. We can divide f by g or g by f, and it looks this way. There's a slight difference between this and the others that we've discussed so far because we have to not only find the intersection of the domains to describe the domain of a quotient function, but we also need to exclude the zeros of g of x. So in other words, think back about our domain discussions previously. We're going to be dividing by one of these two functions, and so whichever values of those functions, whichever values of the function we're dividing by, would cause that function to become 0, have to come out of the domain as well. Because that is one of our domain restrictions that we have found. So let's try an example and you'll see what I mean. We've got f of x equals x squared minus 1, g of x is the square root of x plus 2. We want to do both directions, g divided by f and f divided by g, and we also want to discuss their domains. That might be easier to start with. F of x has a domain from negative infinity to infinity, all real numbers. G of x, though, does have a limited domain because of the square root here. Remember, the radicand, the stuff inside the radical, needs to be non-negative. So remember, we've done that one before. We said that x plus 2 has to be greater than or equal to 0. And solving for x, that gives us the interval including negative 2 up to infinity. So let's actually find those quotients. This one's pretty straightforward. There's not a whole lot to do. If we want to know g divided by f of x, simply divide the two functions, the root function divided by the quadratic function. There's not any simplifying we can do there, really, so we can leave it at that. Again, a reminder of how to find that domain. So in this case, those two numbers that we'd be using to divide by 0, we are going to have to exclude from the domain as well. So in that case, x squared minus 1 is going to be 0 when x is plus or minus 1. You could set that equal to 0 and solve, or try to factor it. That would be easier. X minus 1 times x plus 1. So what that means is we have to take out the numbers negative 1 and positive 1 from the domain. And remember, we've already got a restricted domain from the radical function as well. So we need to start with the interval at negative 2 inclusive, but we can't go straight to infinity there. We have to exclude negative 1 and 1. So we end up with 3 interval pieces, negative 2 to negative 1, skipping over negative 1, up to positive 1, skipping over positive 1, and then going the rest of the way to infinity. Notice we've got, when we divide f by g, a slightly different function. Just divide those two in the other order. Now this time, 1 and negative 1 are okay, but there is another issue with when this denominator is 0, and that would be when x equals negative 2. So the x cannot be negative 2 in this situation when we divide f by g. So we're going to almost use the same domain as g of x itself, but we need to exclude that endpoint of negative 2. So we'll change it to a parentheses to represent an open interval starting at negative 2 going up to infinity. Division's not too bad. There's that little domain thing to consider because we do end up dividing by functions there. But when we talk about this other operation, composition, it gets a little bit more complicated. Not too bad. When we compose two functions together, we're essentially taking the output of one function and putting it into the input area for a different function. And again, this isn't commutative. The order matters, kind of like subtraction and division. So when we compose two functions together, we write that with a little open circle that looks like this. We write f composed with g of x, or f of g of x. That's one way to write it. We can also write it this way, and that's kind of the more logical way, I think, that you'll see it. F of g of x that way. Those two mean exactly the same thing. And so when we want to talk about the domain of those compositions, that is, we use the domain of g to start with, but then we restrict that, we limit that down further based on we can only use the things in the domain of g whose outputs also are in the domain of the outer function, in this case f. So this diagram might help a little, right? We start with an input, we put it into, in this case, the g function first, and then you can kind of see that in parentheses notation there happening on the inside. And then whatever that g of x output is, that's going to be used as input into the f function. And then what we get out is this composition. Let's try an example. I think that'll make it a little bit more clear. We want to determine f of g, and we want to determine its domain. For the domain, we'll look at that real quick first. We start with the domain of the inner function, the one closer to the x, if you want to think of it that way. G of x is going to be the original function we start with, and its domain is -2 to infinity, as we mentioned before. Now, what we have to think about is the range of g of x also. So this is our biggest possible domain now, but we may have to make it smaller depending on the f of x function that we have. So what we need to do is think about what outputs of g of x are we going to be putting into this f function. In other words, if we let x be between -2 and infinity, what is the range of g of x? We know it's 0 to infinity, because if we were to plug in -2, that's going to be our lower endpoint there, we'd get a square root of 0, which is 0. Plugging in a number larger than that will yield a positive number. So the range of g of x is going to start at 0 and go up to infinity. Now, we need to think about f of x also. By itself, ignoring g of x for a second, f of x has unlimited domain, all real numbers, negative to positive infinity. A quadratic function doesn't have any restrictions on it. So that's good news, right? All of those range values that we saw from g of x will still work in the domain. So we can use that domain, that original domain that we mentioned, -2 to infinity, as the domain of the composition. You can kind of test that too, right, by picking a number, and once we've written out the composition, you'll see what I mean. You can choose numbers and test whether they actually exist in the composition or not, and we'll see that. So again, I like to write it this way with the nested parentheses, but your choice, right? F of g of x would look something like this, or f composed with g of x. So all we need to do algebraically to find out what the composition function is, it's pretty easy. We just take g of x and substitute it into the f of x function. So in other words, we're going to replace g of x with square root x plus 2, and we're going to treat that square root x plus 2 as an input into this x for the f of x function. So we end up with the square root of x plus 2 squared minus 1. Simplify that, we could square and square root, those undo each other, so we're left with x plus 2 minus 1, which is x plus 1. Now, this is a little bit strange, because looking at x plus 1, you might think that that domain is all real numbers. However, we already established that there is a restricted domain on this composition, and that's because of the original function with the square root that we used before. If you stop at this step, third from the bottom, you can see why that's true, right? We still have technically a square root here causing a domain restriction. So when we square it to eliminate that square root, that's fine, except we do need to keep in mind our domain issue that we mentioned before. So plugging in a number like -3 would still have no solution here. And so simplifying that can't just get rid of that problem. We need to make note of the domain and remember it that way. Now, real quick, let's do it the other way. Same functions, but other order. G of f is what we're looking for this time. We don't need to worry about the domain for this one, but the idea is that if we do it in the other direction, plug x squared minus 1 in for the x into the g of x function, we'd have g of x squared minus 1, which is the square root of x squared minus 1 plus 2. You could simplify that a tiny bit into the square root of x squared plus 1, but notice that's definitely not the same as the one we found before when we did f of g. Even with the same two functions, you likely won't get the same result each time, depending on the order you choose. Let's take a look at another one. These functions are the square root 1 minus x for f of x, and then g of x is 3x plus 2. If we want to know the f of g of x and also its domain, this time think about what this would look like first. We'll do the composition first and then address the domain things. So our g of x function, that's going to be the one on the inside. That would be like f of g of x like this. And so what we can do, we can plug in g of x into the f function. So we'll do the square root of 1 minus the function 3x plus 2. And then distribute the negative, we're done, right? We've got negative 3x, combining those like terms, -2 plus 1 would become -1. That is our composition function. Now, think about the domain here. We can see that there are going to be some problems because of that radical. So again, starting from the inside, g of x has an infinite domain, all real numbers. The range is also all real numbers. Remember, g of x is just a line. It's a linear function with a slope of 3. So all real numbers for input and output there. Now, this is where we have to be a little careful. Remember, we're looking for the domain of f of x, but we have to remember that we're only using the outputs from g of x in there. So this is where we get a little bit more careful. We have to write not 1 minus x greater than or equal to 0, but we have to write 1 minus the function 3x plus 2 greater than or equal to 0. Distribute our -1 there, and then we will actually solve for x. So we'll combine those constants, add the 1 over to the other side, divide by -3. Make sure when you do that, you flip your inequality sign over. So we have x needs to be less than or equal to -1/3. Which means in interval notation, we go from -infinity up to and including the -1/3 value. You can go back and test that in our composition that we ended up with also. You'll see that numbers less than or equal to -1/3 will exist there, but if we try something bigger, like even 0, you'll end up with a negative radical, which is not okay. One other thing we can do, so we'll talk about how to extend this idea of composition, but then we'll kind of work backwards as well. So as we mentioned, in general, f of g is not the same thing as g of f. We can't do it. We could do either order. Usually they're not the same. We can extend this also to more than 2 functions. So we could compose f with g and h together. This is where that nested parentheses notation makes even more sense to me. I like to write it that way. In this case, we'd be taking the h of x function, plugging those outputs into g of x, then plugging those outputs into f of x. Let's try to break it down and work a little bit backwards too. So in calculus especially, it's useful to be able to break or decompose more complicated functions down into simpler ones. And so an example would be something like the square root of x squared plus 2. Not that complicated, but there are a few different things happening here. If you were to plug a number in for x, think about what you'd need to do to it in the order in order to calculate the output. You'd have to square your number first, then add 2 to it, and then find its square root. So the idea is we want to split those steps that we mentioned, squaring, adding 2, and square rooting. We want to split those into 2 different functions. One possible way to do that would be like this. If we call our f of x function the root x by itself, just the radical part, we call g of x the x squared plus 2 part, so the inside of the radical, then when we compose those together, we get the function we started with. All right, so g of x, remember, if we're writing the composition as f of g of x, then we need to start by doing the operations in g of x first. So this is where we're squaring a number and then adding 2 to it. Once we've done those 2 things, the last thing we need to do is take a square root, and so we're taking the output there and plugging it into the square root function in order to do that. The idea is that we're still doing the same steps in the same order, right? If you were to plug in a number here, you'd be squaring it and then adding 2 and then taking the square root afterward. And that just matches the h of x function that we saw before. Again, often there's more than one way to do it. That's not trivial, so like using f of x equals x or something to just copy the input into the output. Here in this case, remember we said there were 3 operations that needed to be done: a squaring, an adding by 2, and a radical or square root. So what if we split that up the other way? What if g of x was only the x squared piece, and then we, in the f of x function, added 2 and then took a square root? Would that work? Looks like it would, right? If we write f of g of x, remember in this case g of x would just be x squared, so when we plug that into our f of x function, we do still end up with the function h of x that we started with. We have the square root of x squared plus 2. Let's try one of those. So we've got 2 functions, r of x and t of x, and this is like 2 separate problems. We want to split r of x first into 2 functions f and g so that we get f of g of x being equivalent to the original. So for this r of x function, think about the operations. We're subtracting by 3 and we're doing a reciprocal. There, 1 divided by x. And so those are the 2 things we need to do, right? And g of x needs to include, since it's on the inner piece, since that's the function that we're applying first, that needs to have the first operation. That needs to be your x minus 3. If you were to plug that x minus 3 into 1 over x, you'll end up with the function we started with, 1 over x minus 3. And so you can see that here, right? G of x is x minus 3. When we plug that into f, we get 1 over x minus 3, which is back where we started. For t of x, try that one. We have the square root of x squared plus 4. This is kind of like the other example that we saw. One way to do it would be to split it as the square root of x plus 4 for f of x, but then that first step of x squared for g of x. And again, when we compose together, right, g of x becomes x squared, and plugging that in gives us the square root of x squared plus 4, which is what we started with.